Hello, I'm Jonathan Talbot.
I'm Brian Nemsick.
I'm Scott St. Martin.
And I'm Christopher Peterson.
The purpose of our project was to identify moving objects in a stationary camera frame and track them as they move across the frame. If an object we were tracking were to leave the frame and then re-enter, we would attempt to re-identify the object. The first step in our object tracking system is to import the camera frame. After we have the frame, we can subtract out the background, leaving only moving blobs. We can apply filtering to these blobs, after which we know the center of the blob, the area of the blob, and any colors that are in the blob. Using the color data, we can identify if the object represented by the blob has been tracked before, and if it has, we can assign it the same tracking number as the object that was tracked before. The color comparison is only used for objects entering the frame. Otherwise, we use a Hungarian cost assignment matrix algorithm to compare the positions of objects in the current frame to those in the previous frame, allowing us to know which object is which. Lastly, we assign each object a tracking number and plot its track along the camera frame.
The first thing that was implemented was background subtraction. For the first 20 learning frames of the video, we averaged the background. After the first 20 learning frames, we sampled the background every 5 frames. This was because of the rapid changing lighting conditions in the lower portion of the screen. The next step in the processing chain was finding the mask. By subtracting the frame from the background, we could find the movement in the current frame. We then applied a threshold to get a black and white image. This allowed us to see the very beginnings of human movement. One of the major issues with this approach was that as the human walked through the lighted region, he was essentially sliced in half by the light. Instead of having one distinct blob which could be recognized as a human, he was in 2 fragmented sections. Using rudimentary blob detection on that would have led to 2 or 3 tracks for one human during those regions. So from there we had to solve that problem with a unique approach. Our first approach to solving the problem was using black-white distance. Originally we set a threshold value of 12, but that ran into significant issues when you had 2 people walking together. When they were that close, it would just merge the blobs entirely because they were within 10 to 15 pixels of each other. From there we had to come up with a more creative solution. What we ended up doing was an iterative process. We applied a Weiner adaptive noise filter, and then we would BW dist with a 1 pixel difference. And then we'd apply the same process 10 to 15 times to successfully put the blobs together. This allowed us to, 1, put the blobs together, but at the same time not have to worry about if 2 people were walking too closely, having significant overlap, and losing all the information about the separation of tracks. This was probably the hardest part of the project because it was very hard to get one human to appear as one track for the entirety of the video without implementing things that would be a liability later in the project.
Once we had the blob detection working reliably, we could then use it to obtain position data. For each track, we applied a Kalman filter using the center of the blob. The center detection also allowed us to create a bounding box over the moving subject. The area of this box was determined from the blob detection data. The Kalman filter was then used to predict the movement of the blob when certain frames dropped out, or if the subject left the frame completely. Here you can see the Kalman filter predicting the path of the subject after the blob detection has failed. The Kalman filter was used to collect position data for all frames. This data is shown here for all of the detected tracks in an XY versus time plot. One parameter of the Kalman filter that must be chosen is whether to assume a constant velocity or a constant acceleration. For our final result, we chose constant velocity. While the constant acceleration model worked well when a track was detected, it greatly overshot the position when a track left the field of view. Next, we applied a moving average to the track data. Here you can see that this results in a more natural flow to the tracks. Another method that we used to predict the next position of the track was to take the position data that we already had and take the derivative. With the current position data and the velocity data, we can then predict the next location of the track. Here you can see a box plot. You can see that most predicted tracks are within 2 to 6 pixels of the actual track.
One of the major goals of our project was to successfully re-identify targets after they've left the screen. To complete this task, we first grabbed the color histogram data from each of the subframes. Next, we removed the background data from the subframes to isolate the color data only around the blob. This greatly increased the accuracy of the algorithm. In this video, we successfully re-identified a target after it had left the screen. This video showcases the strength of the histogram data, as a new target was identified even though it entered the screen in the same area that target 1 left the screen. To identify a match, we do a dot product between the newly entered subframe and each of the old subframes. Since the dot product of something with itself is 1, a strong match between targets would be a number closer to 1. We incorporate a threshold to successfully identify this match, and if no match is found, a new target is saved.
In the future, we plan on replacing the color histogram functionality with a mixtures of Gaussians that not only takes into account the colors in the blob, but also where those colors are located within the blob. This will allow for more accurate re-identification. Shown is a comparison between the mixture of Gaussians of 2 different targets. It is clear that these targets are not the same person because their mixtures of Gaussians look so different.